Welcome to Milky Narratives. Tonight, leave behind the noise of the waking world, relax your mind, and drift with me into the quietest mysteries of the universe. What if everything you have ever known, every star, every galaxy, every atom in your body, nearly never existed at all? Not because of some cosmic disaster, not because of a black hole, not because of an asteroid, but because the universe itself may have come astonishingly close to never being born. It's a strange thought. When we look around today, existence feels permanent. The earth beneath our feet seems solid. The stars appear eternal. The night sky stretches across unimaginable distances, filled with hundreds of billions of galaxies. It feels as though the universe was always destined to be here, as though everything we see was somehow inevitable. But modern physics paints a very different picture, a far stranger picture, one in which our existence may depend on a chain of events so delicate, so improbable, that even a tiny change in the earliest moments of cosmic history could have erased everything. No stars, no planets, no life, no observers, no one left to wonder why. Tonight we begin our journey at the very edge of existence itself. Not billions of years after the Big Bang, not millions of years before humanity, but in the first tiny fraction of a second when reality was just beginning to emerge. To understand how extraordinary our universe truly is, we first need to appreciate something surprising. The universe did not begin as the peaceful sea of stars we see today. It began in chaos, extreme chaos. Temperatures were so high that atoms could not exist. In fact, even the particles that would later form atoms could not survive for long. Energy and matter transformed into one another continuously. Space itself expanded at incredible rates. The laws of physics that govern our everyday lives were hidden beneath conditions so violent that they seem almost impossible to imagine. And yet, despite this chaos, something remarkable happened. The universe survived. That statement may sound obvious. After all, we're here. But survival was not guaranteed. In many of our most advanced theories, there are countless ways a universe can fail. Some universes may collapse almost immediately after they form. Others may expand too rapidly for structures to ever develop. Some may never produce stars. Some may never create chemistry. Some may remain nothing more than lifeless clouds of radiation forever. Our universe appears to have avoided all of those outcomes, and the deeper scientists investigate, the more astonishing that fact becomes. Consider gravity. If gravity were slightly stronger, matter might collapse too quickly into black holes. Stars could burn too fast. Galaxies might become unstable. If gravity were slightly weaker, matter might never gather together at all. No stars, no planets, no cosmic structures. Just a thin, cold fog of particles drifting endlessly through space. Now consider the electromagnetic force. The force responsible for atoms, chemistry, molecules, and ultimately life itself. If its strength differed by even a small amount, the chemistry required for complex structures could become impossible. Atoms might never form, or they might become unstable. The universe could remain forever barren. Then there is the strong nuclear force, the force that binds protons and neutrons together inside atomic nuclei. A tiny adjustment to its strength could prevent stars from manufacturing the heavier elements that make planets and living organisms possible. No carbon, no oxygen, no iron, no biological life, no human beings wondering about the cosmos. Again and again, physicists encounter this unsettling pattern. The universe seems balanced on a knife's edge. Many of the numbers that govern reality appear to fall within extremely narrow ranges that allow complexity to exist. Change them slightly, and the story unfolds very differently. Of course, this raises an enormous question. Was this balance simply luck, or is there some deeper principle we have not yet discovered? Scientists do not yet know. And that uncertainty is one of the reasons cosmology remains such an exciting field. Every answer seems to reveal a deeper mystery beneath it. But the story becomes even stranger, because the fine-tuning of physical laws is only part of the puzzle. There is another mystery hiding in plain sight, a mystery so profound that it affects every galaxy, every star, and every living thing in existence. According to our best understanding of physics, the universe should not contain this much matter at all. In fact, it may not have contained any. When energy transforms into particles, it typically produces matter and antimatter together, equal amounts, perfect symmetry. And if that symmetry had remained intact, the universe would have experienced a catastrophic mutual annihilation. Matter and antimatter would have destroyed each other. The result? A universe filled only with radiation. No galaxies, no planets, no life. Nothing resembling the cosmos we know today. Yet somehow, somewhere in the earliest moments of time, that perfect balance was broken. A tiny excess of matter survived. Just enough. Enough to form the first atoms. Enough to build the first stars. Enough to create every galaxy scattered across the observable universe. Enough to create you. The entire visible cosmos may owe its existence to an imbalance so small that it is almost difficult to comprehend. And this realization leads us toward one of the greatest mysteries in modern science. Why did anything survive at all? Why is there something rather than nothing? The answer may lie hidden within the earliest moments of cosmic history, buried beneath layers of physics that we have only begun to explore. And as we continue our journey, we will discover that the universe was not merely born. It may have escaped destruction by the smallest margin imaginable. 2. The first second was more dangerous than any black hole. Long before stars were born, the universe survived conditions so extreme that physics itself nearly broke apart. When most people imagine the beginning of the universe, they picture an enormous explosion, a flash of light, a burst of energy, a moment when everything suddenly appeared. But the reality is far stranger. The earliest universe was not simply hot. It was not simply dense. It existed in a state so extreme that many of the concepts we rely on to understand reality today may not have existed at all. There were no stars, no galaxies, no planets, no atoms, not even the building blocks of atoms. There was only a seething ocean of unimaginable energy, a realm where temperatures exceeded anything nature would ever produce again. A realm where the laws of physics themselves approached their limits. And for a brief moment, reality stood at the edge of something we still do not fully understand. To appreciate just how dangerous the first second truly was, we need to shrink our perspective far beyond anything human intuition can grasp. Imagine taking the entire observable universe, every galaxy, every star, every black hole, every planet, every particle. Now compress all of it into a region smaller than a single atom. Then make it hotter than the core of every star that will ever exist combined. Even that description barely captures the conditions of the early cosmos. At the beginning, the universe was so dense that matter could not survive. Particles collided with such enormous energies that they constantly transformed into other particles. Nothing remained stable for long. Everything emerged and vanished in an endless storm of creation and destruction. Today, the universe feels calm. A photon can travel across millions of light years without encountering anything at all. But in those first moments, there was no emptiness, no peaceful void. Every point in space was flooded with energy. Every fraction of a second brought violent interactions on scales beyond imagination. And yet, the greatest danger was not the heat, nor the density, nor even the violence. The greatest danger was that the laws of nature themselves may not have been fully formed. This is one of the strangest ideas in modern physics. The forces we experience today, gravity, electromagnetism, the strong nuclear force and the weak nuclear force, appear distinct. Each governs a different aspect of reality. But as scientists peer further back toward the beginning, evidence suggests these forces may once have been united. A single force, a deeper symmetry, a more fundamental state of nature. In the unimaginably hot environment of the infant universe, the distinctions between these forces may have disappeared entirely. The universe was so energetic that the familiar rules governing matter could no longer operate in their modern form. Reality itself may have existed in a radically different phase, a phase unlike anything we observe today. Then, as the universe expanded and cooled, something remarkable happened. The forces began to separate. Like water freezing into ice, the cosmos underwent a series of transitions. One unified force became many. The laws of nature crystallized into the forms we recognize today. Gravity went one way, the nuclear forces went another. Electromagnetism emerged with its own identity. The universe began organizing itself. But phase transitions can be dangerous. Even here on Earth, dramatic transitions occur when water freezes or boils. Now imagine a phase transition affecting the entire universe. A transformation involving all of space itself. Tiny fluctuations during these moments could be amplified enormously. Regions could evolve differently. Instabilities could appear. Entire cosmic futures could depend on microscopic quantum events. And some physicists believe the universe may have come astonishingly close to disaster. According to certain theories, our universe may currently exist in what is called a false vacuum, a state that appears stable but may not be the absolute lowest energy configuration possible. Think of a marble resting in a shallow valley. From its perspective, everything seems secure. But somewhere nearby exists a deeper valley. If the marble ever finds a path downward, everything changes. Applied to the universe, the implications are extraordinary. If a lower energy vacuum state exists, a quantum fluctuation could theoretically trigger a transition. A bubble of true vacuum would form and begin expanding at nearly the speed of light. Inside that bubble, the laws of physics could be completely different. Atoms might not exist. Stars might never form. Life would become impossible. Everything we know could vanish instantly. Fortunately, if such a danger exists, it appears incredibly unlikely. The universe has survived for nearly 14 billion years. Yet the possibility reminds us of something profound. Reality is not as solid as it feels. Beneath the familiar surface of existence lies a landscape of astonishing complexity, and nowhere was that complexity more extreme than during the first second. As the universe continued expanding, temperatures gradually fell. The cosmic storm began to calm. The most energetic particles disappeared. The rapid transformations slowed. For the first time, the foundations of structure could begin to emerge. But another challenge waited ahead, one that would prove just as important as all the violence that came before. The universe needed to create matter. Not equal amounts of matter and antimatter, not perfect symmetry. It needed an imbalance, a tiny imperfection, a flaw so small that it would have been invisible amid the chaos. And yet, without that flaw, none of us would be here. Somewhere within that first second, while the universe was still hotter than any star and denser than any black hole, something happened. A subtle asymmetry appeared, a preference, a slight tilt in the cosmic scales. For every billion pairs of matter and antimatter particles, there may have been just one extra particle of matter. One. That tiny excess sounds insignificant, almost laughably small, but it changed the fate of the cosmos. When matter and antimatter later annihilated one another, nearly everything disappeared into pure energy. Nearly everything. Those extra particles survived, and from those survivors came every star, every galaxy, every planet, every living thing, every thought, every dream, every question humanity has ever asked. The universe did not need a large advantage. It only needed the smallest imbalance imaginable, and somehow, against all odds, it got one. The deeper physicists investigate these first moments, the stranger the story becomes. The universe was not born into stability. It fought for it. It passed through phases of unimaginable violence. It endured temperatures beyond comprehension. It survived transitions that reshaped the laws of nature. And somewhere within that chaos, reality found a path forward. A path so narrow that had even one step gone differently, the cosmos we know today might never have emerged. The stars above us seem eternal. The galaxies seem permanent. But their existence may trace back to a fragile victory won during the first second of time itself. And the deeper we look into that first second, the more we begin to realize that the greatest mystery is not how the universe evolved afterward. The greatest mystery may be how it survived at all. 3. Why there is something instead of nothing. According to modern physics, the universe should have destroyed itself in its first moments. That statement sounds almost impossible. After all, the evidence of existence is everywhere. The stars shine above us. Galaxies fill the observable universe. Planets orbit distant suns. Life emerged on at least one small world. And somehow, conscious beings evolved that can sit quietly at night and wonder how any of this happened. Existence feels undeniable. Yet when physicists look back toward the earliest moments of cosmic history, they encounter a paradox, a contradiction buried deep within the laws of nature, a contradiction that suggests the universe as we know it should not exist. To understand why, we need to return once again to the first moments after the Big Bang. The universe was unimaginably hot. Energy filled every corner of reality. And wherever enough energy exists, nature can perform one of its strangest tricks. It can create matter. But there is a catch. Nature rarely creates matter alone. Instead, it produces matter and antimatter together. Perfect pairs, a particle and its mirror image. For every electron, a positron. For every proton, an antiproton. For every particle, an opposite. At first glance, antimatter sounds like something from science fiction, but it is very real. Scientists create antimatter particles in laboratories. We observe them in cosmic rays. Their existence is one of the most thoroughly confirmed discoveries in modern physics. And antimatter behaves almost exactly like ordinary matter. Almost. The crucial difference is what happens when matter and antimatter meet. They annihilate, completely. Their mass is converted into pure energy. Nothing remains. Imagine two snowflakes touching and instantly becoming light. That is closer to the truth than it might seem. Whenever matter encounters antimatter, both disappear in a flash of energy. Now imagine the infant universe, a place where particles and antiparticles were being created continuously. Everywhere, every instant, an endless cosmic dance of creation and destruction. According to our best theories, the Big Bang should have produced matter and antimatter in equal quantities. Perfect balance, perfect symmetry. And if that happened, the outcome appears straightforward. Matter and antimatter would eventually annihilate one another. Everything would vanish. The universe would become little more than a sea of radiation. No stars, no galaxies, no planets, no life, no observers. Nothing resembling the cosmos we see today. And yet clearly that is not what happened. Somehow, something interrupted the symmetry. Somewhere during those earliest moments, nature chose a side. Not dramatically, not overwhelmingly, just enough. Imagine lining up 1 billion matter particles beside 1 billion antimatter particles. Now add a single extra matter particle, just one. When annihilation occurs, nearly everything disappears, but that lone survivor remains. At first, it seems insignificant, meaningless, a tiny leftover particle floating through a sea of radiation. But multiply that process across the entire universe, repeat it everywhere, and suddenly those survivors become important, extraordinarily important. Every galaxy we observe today, every star that has ever shined, every planet that has ever formed, every living organism that has ever existed, all of it may descend from those tiny survivors. The entire visible universe could be the result of an imbalance so small that it is difficult to imagine, a difference of roughly one particle in a billion. And this is where the mystery deepens. Physicists have spent decades trying to understand why this imbalance occurred. Why did matter gain the advantage? Why wasn't symmetry preserved? Why did anything survive at all? The truth is that nobody knows with certainty. There are theories, many theories. Some suggest that subtle violations of symmetry occurred during the early universe. Others propose entirely new particles that have yet to be discovered. Some ideas involve processes that unfolded fractions of a second after the Big Bang. Others point toward physics beyond the standard model. Yet despite enormous progress, the ultimate answer remains elusive. And perhaps that is what makes the question so fascinating. The deeper we investigate existence, the less inevitable it appears. For centuries, humanity assumed the universe simply existed. The stars were there, the earth was there, reality was there. The question seemed almost trivial. But modern cosmology reveals a much stranger picture. Existence may be balanced upon an incredibly delicate foundation, a foundation built from tiny asymmetries and improbable events. the universe appears less like an unavoidable outcome and more like a narrow pathway through countless possibilities. And that realization naturally leads to another question. What do we actually mean by nothing? It sounds like a simple concept, an empty void, a complete absence of existence. No matter, no energy, no space, no time. Nothing. Yet modern physics has transformed even this seemingly straightforward idea into a profound mystery. Because when physicists examine empty space, they do not find true nothingness. Instead, they find activity, fluctuations, quantum fields, invisible processes constantly occurring beneath reality. Even a perfect vacuum is not truly empty. Particles can briefly appear and disappear. Energy fluctuations ripple through the fabric of space itself. The universe, it seems, refuses to remain still. This discovery has forced scientists to reconsider one of the oldest questions ever asked. Can absolute nothingness actually exist? Or is nothing itself unstable? Could the universe have emerged from a quantum state that appears empty but contains hidden potential? Some physicists believe so. Others remain skeptical. The debate continues. But regardless of which explanation ultimately proves correct, one fact remains astonishing. The existence of something rather than nothing may not be a simple fact. It may be one of the deepest mysteries in all of science. Tonight, as you listen to these ideas, it is worth pausing for a moment to appreciate how extraordinary existence truly is. Every atom in your body traces its history back to the earliest moments of cosmic time. Every breath you take depends on stars that lived and died billions of years ago. Every thought moving through your mind is possible because matter survived when by all appearances it should have vanished. You are part of the answer to a question that humanity still struggles to understand. Why is there something instead of nothing? Perhaps one day science will uncover the full story. Perhaps future generations will discover the mechanism that tipped the balance in favor of existence. Or perhaps the mystery will only deepen as our knowledge expands. Because throughout history, every major discovery has revealed new questions waiting beyond the horizon. And as we continue our journey through the cosmos, we will encounter another astonishing realization. The universe did not merely survive, it expanded, at a speed so extraordinary that it transformed reality itself and set the stage for everything that would come afterward. But that is a story for the next chapter. If you're still awake, leave a comment telling me what mystery about existence keeps you awake at night. 4. The tiny imbalance that created everything. A difference smaller than one particle in a billion may be the reason galaxies exist today. At first, that sounds absurd. How could something so unimaginably small determine the fate of an entire universe? How could a discrepancy so tiny shape every galaxy, every star, every planet, and every living thing that would eventually emerge? Yet modern cosmology suggests exactly that. In fact, if this imbalance had been even slightly smaller, you would not be listening to these words right now. There would be no Earth, no Milky Way, no atoms, no life. Only darkness and radiation stretching endlessly through space. The entire history of existence may depend on one of the smallest asymmetries nature has ever produced. As we discovered in the previous chapter, the early universe appears to have generated slightly more matter than antimatter. Not much more. Not millions of extra particles, not even thousands. Only a tiny excess. Roughly one additional matter particle for every billion matter-antimatter pairs. To understand how astonishingly small that difference is, imagine collecting 1 billion grains of sand on a beach. Now add a single extra grain. If you stepped back and looked at the pile, you would never notice the difference. It would seem perfectly balanced, perfectly symmetrical. Yet in the infant universe, that microscopic imbalance changed everything. As matter and antimatter collided, they annihilated one another in vast quantities. Nearly all of it disappeared. The universe became flooded with energy. Particle after particle vanished. Antiparticle after antiparticle vanished. For a brief period, it seemed as though existence itself might be erased. But then something remarkable happened. The annihilations slowed. The temperature continued to fall, and those extra matter particles remained behind, tiny survivors of an unimaginable cosmic war. Everything that exists today descends from those survivors. Every mountain, every ocean, every tree, every animal, every human being, every civilization, every dream humanity has ever dreamed. The entire visible cosmos emerged from that slight imbalance. And yet, despite decades of research, scientists still do not fully understand why it happened. This mystery has a name: baryogenesis, the origin of matter itself. It is one of the greatest unsolved problems in modern physics, because according to many of our equations, matter and antimatter should have been created in exactly equal quantities. Symmetry should have prevailed. Nothing should have survived. Yet clearly something broke that symmetry. Some process favored matter over antimatter. Some event tilted the scales. Some hidden mechanism gave existence a chance. But what was it? To answer that question, physicists have spent decades recreating conditions similar to those of the early universe. They smash particles together at enormous energies. They search for subtle asymmetries in nature. They examine how particles decay. They study the smallest building blocks of reality. And occasionally they find hints, tiny clues that suggest nature may not be perfectly symmetrical after all. One example comes from something known as CP violation. The name sounds technical, but the basic idea is surprisingly simple. Imagine watching a process occur. Then imagine replacing every particle with its antiparticle and viewing the event in a mirror. If nature were perfectly symmetrical, both versions should behave identically. But experiments reveal that this is not always true. Certain particles exhibit slight preferences, tiny biases, subtle departures from perfect balance. At first glance, these effects seem insignificant. But in the early universe, even the smallest bias could have enormous consequences. A slight preference repeated trillions upon trillions of times may have been enough to generate the excess matter we observe today. Yet there is a problem. The amount of CP violation currently observed appears too small, far too small. It cannot fully explain the abundance of matter in the modern universe, which means there may be additional physics still waiting to be discovered. Something hidden, something beyond our current theories. And this realization opens the door to fascinating possibilities. Perhaps unknown particles once existed in the infant universe, particles that vanished long ago. Perhaps entirely new forces influenced cosmic evolution. Perhaps reality contains layers we have not yet uncovered. Every answer seems to lead to deeper questions. But there is another perspective that makes this mystery even more astonishing. Consider the universe before galaxies existed, before stars illuminated the darkness, before planets formed, before chemistry emerged. The universe was almost perfectly smooth. Almost. If we could travel back and observe it shortly after the Big Bang, we would see a remarkably uniform sea of matter and radiation. No galaxies, no clusters, no giant structures. Just an incredibly even distribution spread across space. And yet hidden within that smoothness were tiny fluctuations, tiny variations in density, regions that contained ever so slightly more matter than their surroundings, differences so small that they amounted to only fractions of a percent. At first, these fluctuations seemed insignificant, but gravity is patient. Gravity does not need dramatic advantages. It only needs time. Over millions of years, regions with slightly more matter exerted slightly stronger gravitational pull. They attracted additional material. As they grew larger, their gravity became stronger still. The process fed upon itself. Tiny fluctuations became larger structures. Larger structures became clouds. Clouds became galaxies. Galaxies gathered into clusters. Clusters assembled into vast cosmic webs stretching across billions of light years. The magnificent universe we observe today emerged from minute imperfections. In a sense, the cosmos owes its beauty not to perfection, but to flaws. If the early universe had been perfectly smooth, galaxies might never have formed. Stars might never have ignited. Life might never have appeared. The structures we admire today exist because reality was slightly imperfect. And perhaps there is something profound in that realization. Nature often seems to favor balance, yet complete perfection can be surprisingly sterile. A perfectly smooth universe remains empty. A perfectly symmetrical universe destroys itself. A perfectly uniform cosmos produces no structure. It is the tiny imperfections that create complexity, the tiny asymmetries that allow evolution, the tiny fluctuations that give rise to beauty. Even on Earth, many of the most extraordinary phenomena emerge from small differences. A slight change in temperature creates weather systems. Tiny genetic mutations drive biological evolution. Small variations in landscape shape entire ecosystems. Again and again, complexity arises from imperfection. The universe itself may be the ultimate example. And this brings us back to a question that scientists continue to wrestle with today. Was this imbalance merely an accident, or was it inevitable? Did our universe simply get lucky, or do deeper laws guarantee that matter will always gain the advantage? At present, nobody knows. Perhaps future discoveries will reveal the answer. Perhaps new particle accelerators will uncover hidden physics. Perhaps entirely new theories will emerge. Or perhaps the mystery will prove even stranger than we currently imagine. But regardless of the ultimate explanation, one fact remains extraordinary. Every star in the night sky, every galaxy beyond the horizon, every atom inside your body, every thought passing through your mind, exists because nature favored matter by the tiniest of margins. A difference smaller than one particle in a billion, a microscopic imbalance. A flaw so small it seems almost invisible. And yet that flaw transformed an empty universe into one filled with galaxies, planets, life, and wonder. As our journey continues, we will discover that this was not the only improbable event in cosmic history. Because shortly after these tiny imbalances appeared, the universe experienced something even more astonishing. An expansion so sudden, so violent, and so extraordinary that it changed the size of reality itself. And without it, the cosmos we know today might never have existed. 5. The cosmic battle between matter and antimatter. In the beginning, the universe may have been a battlefield where almost everything annihilated itself. When we look up at the night sky today, it is easy to imagine the universe as a peaceful place. Stars glow quietly in the darkness. Galaxies drift through space over billions of years. Planets circle their suns with almost clockwork precision. From a human perspective, the cosmos appears calm, ancient, stable, almost eternal. But the early universe was nothing like that. If we could travel back to the first moments after the Big Bang, we would not find tranquility. We would find chaos, violence beyond imagination, a reality so energetic and unstable that existence itself seemed uncertain. And at the center of this chaos was one of the greatest battles in cosmic history, the battle between matter and antimatter, a conflict that determined whether anything would exist at all. Because long before galaxies formed, long before stars ignited, long before planets cooled, the universe faced a simple but devastating problem. Every time it created matter, it also created antimatter. At first glance, antimatter seems almost magical, something invented by science fiction writers, something that belongs in futuristic spaceships or alternate universes. Yet antimatter is completely real. Scientists have produced it in laboratories. They observe it emerging from powerful particle collisions, and according to the laws of physics, antimatter should be everywhere. In fact, if symmetry had prevailed, the universe should contain equal amounts of matter and antimatter today. But it does not, and that discrepancy remains one of the greatest mysteries in modern science. To understand why, imagine a universe moments after the Big Bang. Temperatures exceed anything that will ever naturally occur again. Space is flooded with energy. Particles appear continuously. Electrons, quarks, neutrinos, and alongside every one of them, their antimatter counterparts, positrons, antiquarks, antineutrinos. The universe is producing both sides of reality simultaneously. Matter and antimatter emerge together like reflections in a mirror. Perfect symmetry, perfect balance, at least initially. Now imagine what happens when these opposites meet. An electron encounters a positron. Instantly, both vanish. A proton meets an antiproton. Again, both disappear. Mass transforms into pure energy. Nothing survives. The process is astonishingly efficient. There are no fragments, no leftovers, no debris. Just energy, pure radiation spreading through space. This is what makes the mystery so profound. If the universe created equal amounts of matter and antimatter, then almost everything should have annihilated itself. And for a while, that is exactly what happened. The early cosmos became a colossal battlefield. Everywhere, particles collided with their opposites. Everywhere, annihilation erupted. Matter disappeared, antimatter disappeared. Energy flooded the universe. Imagine a cosmic war so complete that nearly every participant is destroyed. Not armies, not civilizations, not planets, but the fundamental building blocks of reality itself. For a brief period, existence balanced on the edge of oblivion. And if symmetry had remained perfect, the battle would have ended with total mutual destruction. No winners, no survivors, no future. Yet somehow, the story unfolded differently. Matter gained the slightest advantage. Not enough to dominate immediately, not enough to be obvious, just enough to survive. Imagine a battlefield containing 1 billion soldiers on each side. After the fighting ends, every combatant is gone except a single survivor. One lone individual standing amid unimaginable destruction. That lone survivor determines the future. In many ways, this is exactly what happened in the early universe. For roughly every billion matter-antimatter pairs, one extra matter particle remained. Just one. It sounds insignificant, almost laughably small, but that survivor changed everything. Because while annihilation destroyed almost all matter and antimatter, it could not destroy that final excess. Those particles remained behind as the universe continued expanding and cooling. Tiny remnants, tiny survivors, tiny seeds from which everything else would eventually grow. Every atom in your body traces its ancestry back to those survivors. Every star that shines in the night sky exists because of them. Every galaxy scattered across billions of light years emerged from that tiny advantage. In a very real sense, the universe we know is the aftermath of an ancient battle that matter barely won. And perhaps the strangest part is that we still do not fully understand why it won. Physicists often describe science as a process of uncovering deeper layers of reality. But occasionally we encounter questions that seem to become more mysterious the closer we examine them. This is one of those questions. Why did matter survive? Why not antimatter? Why wasn't the balance exact? Nature appears remarkably symmetrical in many ways. The laws governing particles often treat matter and antimatter similarly. Yet somewhere in the earliest moments of cosmic history, a subtle asymmetry emerged. A preference, a tiny imbalance, a slight tilt in the scales of existence. And that tilt changed everything. Scientists have spent decades searching for clues. Particle accelerators probe deeper into the structure of matter. Experiments measure the behavior of subatomic particles with astonishing precision. Observatories examine the oldest light in the universe. Again and again, researchers search for evidence that might explain the imbalance. And yet the complete answer remains elusive. Some theories suggest entirely new particles existed shortly after the Big Bang. Others propose hidden interactions that operated only under extreme conditions. Some models invoke massive particles that vanished long ago, leaving only indirect traces behind. Each possibility offers part of the puzzle, but none have solved it completely. And that uncertainty is what makes cosmology so fascinating. The deeper we look, the more extraordinary existence appears, because the universe was not merely handed a future, it earned one. Against overwhelming odds, against near-perfect symmetry, against a process that should have erased everything, matter somehow survived. But the story becomes even stranger when we consider another question. If antimatter once existed in such abundance, where is it now? Why don't we see entire antimatter galaxies? Why aren't there antimatter stars shining somewhere beyond our telescopes? The answer seems to be that the annihilations were incredibly thorough. Most antimatter vanished during those early cosmic battles. Today, naturally occurring antimatter exists only in tiny amounts, produced in high-energy events, generated by radioactive decay, created in powerful astrophysical environments. The vast antimatter populations of the early universe appear to be gone, destroyed billions of years ago, leaving behind only matter, leaving behind us. And yet, traces of that ancient struggle still surround us. Every photon of light carries evidence of processes that unfolded during the infancy of the cosmos. Every galaxy contains matter that survived those first moments. Every atom serves as a reminder that existence was not guaranteed. The stars above us are monuments to a narrow victory, a victory measured not in armies or empires, but in particles. A victory so slight that it amounted to one extra survivor in a billion. And perhaps that is one of the most humbling lessons modern cosmology offers. The universe did not emerge from certainty. It emerged from improbability, from tiny fluctuations, from fragile imbalances, from events that could easily have unfolded differently. Had the scales tipped the other way, there would be no galaxies to admire, no planets to explore, no life to evolve, no minds capable of asking these questions. But the scales did tip. Matter survived. The battle ended. And from its survivors emerged everything we know. Yet another mystery was already waiting. Because while matter had won its war against antimatter, the universe itself was about to undergo a transformation even more dramatic. A transformation so extraordinary that space would expand faster than light itself. A moment that would stretch the infant cosmos from microscopic scales to unimaginable size in less than the blink of an eye. And that astonishing event is where our journey leads next. 6. Why empty space isn't actually empty. The emptiest regions of the cosmos may be boiling with invisible activity right now. When most of us imagine empty space, we picture nothing, a perfect void, a silent black expanse stretching endlessly between the stars. No matter, no light, no sound, no activity, just emptiness. It seems like one of the simplest concepts imaginable. After all, if you remove everything from a room, the furniture, the air, the dust, even the atoms, you are left with nothing, or so it would seem. Yet one of the strangest discoveries in modern physics is that true emptiness may not exist at all. In fact, the deeper scientists investigate the nature of space itself, the more mysterious it becomes. What appears empty may actually be one of the most active environments in the entire universe. Invisible, restless, alive with fluctuations occurring beyond human perception. And if that idea sounds surprising, it becomes even more astonishing when we realize that these hidden activities may have shaped the entire cosmos, including you. To understand why, imagine drifting through one of the vast cosmic voids that lie between galaxy clusters. These regions are among the emptiest places known. Some stretch hundreds of millions of light years across. Galaxies are rare. Stars are absent. Matter is incredibly sparse. Compared to Earth, these regions seem unimaginably empty. And yet, according to quantum physics, even there, space is not truly vacant. Something remains, something unavoidable. For centuries, scientists believed that a vacuum represented the complete absence of everything, an empty stage upon which the drama of the universe unfolded. Space was merely a backdrop, a passive container, a vast emptiness through which matter moved. But during the 20th century, that picture began to change. Physicists discovered that reality operates according to quantum laws, and quantum laws are strange, very strange. At the quantum level, certainty begins to dissolve. Particles behave like waves. Objects exist in probabilities rather than fixed states, and even emptiness refuses to remain empty. One of the central principles of quantum mechanics is known as the uncertainty principle. In simple terms, nature imposes limits on how precisely certain quantities can be known simultaneously. The universe does not allow perfect certainty, and one consequence of this principle is extraordinary. Energy itself can briefly fluctuate, even in a vacuum, even in apparently empty space. This does not mean that particles suddenly appear from nowhere and remain forever. Instead, tiny fluctuations emerge and vanish almost instantly. For unimaginably brief moments, particle pairs can materialize from the quantum vacuum, then disappear again before violating the laws of physics. The process occurs so quickly that it remains invisible to ordinary experience. Yet according to our best theories, it is happening constantly, everywhere, all around us, even now. The vacuum is not silent. It is humming with activity, a restless sea of possibilities bubbling beneath reality. Sometimes physicists describe these temporary entities as virtual particles. The name can be misleading. They are not imaginary, nor are they particles in quite the same sense as ordinary matter. Rather, they are manifestations of quantum fields fluctuating throughout space. And their existence is not merely theoretical. We have observed their effects. Experiments reveal subtle shifts in atomic behavior caused by vacuum fluctuations. The so-called Casimir effect demonstrates that empty space can exert measurable forces. Even the properties of particles themselves appear influenced by the activity of the quantum vacuum. Again and again, nature reveals the same astonishing truth. Empty space is not empty. The void is alive with hidden structure. And this realization forces us to rethink one of the oldest assumptions about existence. If even nothing contains activity, then what exactly do we mean by nothingness? The question sounds philosophical, but it has become deeply scientific. Because the closer we examine the foundations of reality, the harder true nothingness becomes to define. Imagine removing every star, every galaxy, every atom, every particle, every form of matter and energy. What remains? At first glance, the answer seems obvious. Nothing. Yet quantum physics suggests otherwise. Even if all particles vanished, the underlying quantum fields would remain. The fabric of spacetime would remain. The laws governing fluctuations would remain. The possibility of activity would remain. And so physicists find themselves confronting a profound puzzle. Perhaps absolute nothingness is impossible. Perhaps reality naturally generates structure. Perhaps the vacuum itself contains the seeds of existence. This idea lies at the heart of some modern theories about the origin of the universe. Certain models propose that our cosmos emerged from quantum fluctuations within a primordial vacuum state. Not a vacuum in the everyday sense, not an empty box, but a quantum vacuum filled with latent potential, a state that appears empty while secretly containing the ingredients necessary for creation. In this picture, the universe did not emerge from absolute nothingness. It emerged from a deeper level of reality, a level where fluctuations are unavoidable, a level where existence can spontaneously arise. Scientists continue debating these ideas. The evidence remains incomplete. Many questions remain unanswered. Yet the possibility is extraordinary. The galaxies we see today may trace their origins to tiny quantum fluctuations that occurred billions of years ago. Fluctuations so small they would be impossible to detect directly. Tiny irregularities in the infant universe. Tiny differences in density. Tiny wrinkles in the fabric of reality. And yet those tiny fluctuations became the seeds of cosmic structure. As the universe expanded, gravity amplified them. Regions containing slightly more matter attracted additional matter. Small variations became larger. Larger structures became galaxies. Galaxies became clusters. Clusters became vast cosmic webs stretching across the observable universe. The stars overhead, the Milky Way, the Earth, every living thing. All may ultimately trace their origins back to microscopic quantum fluctuations emerging from what once appeared to be empty space. It is a breathtaking idea. The largest structures in existence emerging from the smallest fluctuations imaginable. The universe transforming quantum uncertainty into galaxies. Possibility becoming reality. And perhaps there is something beautiful hidden within that story, because on human scales, we often seek stability, certainty, predictability. Yet the cosmos seems built upon something very different. Beneath the appearance of order lies uncertainty. Beneath apparent emptiness lies activity. Beneath stillness lies motion. The universe is not static. It is dynamic at every level. Even where we expect nothing, something is happening. And perhaps that is one of the deepest lessons modern physics offers. Reality is richer than it appears. The darkness between galaxies is not truly empty. The vacuum is not truly silent. The void is not truly nothing. Instead, space itself may be an active participant in the story of existence. A hidden ocean whose waves shaped the cosmos long before stars began to shine. Yet this realization introduces an even more astonishing mystery. If empty space contains energy, if the vacuum itself possesses hidden properties, then that energy should influence the expansion of the universe. And when astronomers began measuring that expansion with increasing precision, they discovered something utterly unexpected, something that changed cosmology forever. The universe was not simply expanding, it was accelerating, as though empty space itself possessed a mysterious power pushing galaxies apart, a power we now call dark energy. And understanding that mysterious force may reveal even deeper secrets about the true nature of reality. 7. The strange quantum ocean beneath reality. What we call nothing might secretly be one of the most active things in existence. For thousands of years, human beings imagined emptiness as the ultimate absence, a place where nothing happens, a place where nothing exists, a place beyond all activity, all structure, and all possibility. The concept seemed so obvious that few people questioned it. After all, if you remove every star from the sky, every atom from space, every particle from existence itself, what could possibly remain? Surely the answer is nothing. And yet, the deeper science investigates reality, the stranger the answer becomes, because modern physics suggests that emptiness may not be empty at all. In fact, what we casually call nothing may be more active than the surface of a star, more dynamic than a hurricane, more chaotic than the most violent explosion in the universe. Not on human scales, not in ways our senses can perceive, but deep beneath reality itself, at the quantum level, hidden beneath everything we know. To understand this idea, imagine standing on the shore of a vast ocean. At first glance, the water appears calm, smooth, peaceful, almost motionless. But beneath the surface, countless currents move in every direction. Waves collide, pressure shifts, energy flows continuously through the system. The apparent stillness is an illusion. The ocean is alive with activity. According to quantum physics, reality may work in a similar way. The universe appears stable because our human senses operate on large scales. We see planets, stars, galaxies, objects that persist through time. But beneath those familiar structures lies something far stranger, a hidden quantum ocean. An invisible realm where fluctuations occur constantly, a realm where particles emerge and disappear, where probabilities replace certainties, where reality itself seems to shimmer with possibility. One of the most revolutionary discoveries of 20th century physics was that particles are not the deepest layer of existence. For centuries, scientists searched for smaller and smaller building blocks: atoms, electrons, protons, neutrons, quarks. Each discovery seemed to reveal a deeper level of structure. But eventually, physicists realized something astonishing. The universe may not fundamentally consist of particles at all. Instead, it may consist of fields. Invisible fields that extend throughout all of space, everywhere, at all times. According to quantum field theory, electrons are not tiny balls flying through empty space. They are excitations of an electron field. Photons are excitations of an electromagnetic field. Quarks arise from their own fields. Every known particle emerges from an underlying quantum field. In this picture, the universe resembles an immense ocean. The fields are the water. Particles are the waves. And what we call empty space is simply the ocean in its lowest energy state. But even the calmest ocean is never perfectly still. Tiny ripples remain. Tiny fluctuations continue. And this is where the story becomes truly remarkable. Quantum fields can never be completely motionless. The uncertainty principle prevents perfect stillness. There is always some residual activity, some background fluctuation, some unavoidable motion woven into the fabric of reality itself. The vacuum seethes with energy, not enough to produce visible fireworks, not enough to create stars spontaneously, but enough to ensure that empty space remains fundamentally active. Even now, as you listen, as the Earth rotates beneath the night sky, as distant galaxies drift through the darkness, the quantum vacuum is fluctuating. Invisible processes are unfolding everywhere around you. And perhaps most astonishingly, these fluctuations are not merely mathematical abstractions. They have consequences, real consequences. Consequences we can measure. Consequences that may have shaped the entire universe. To see how, we must travel back to a time before stars existed, before galaxies formed, before matter organized itself into anything recognizable, back to the earliest moments of cosmic history. At that time, the universe was incredibly small, incredibly hot, and incredibly young. Yet even then, quantum fluctuations existed. Tiny variations in energy, tiny irregularities in the vacuum, tiny differences scattered across the infant cosmos. At first, these fluctuations were unimaginably small, far smaller than atoms, far smaller than anything we could ever observe directly. But something extraordinary happened. The universe expanded, rapidly, violently, on scales beyond ordinary comprehension. And as it expanded, those microscopic fluctuations were stretched across enormous distances. Tiny quantum irregularities became cosmic seeds, seeds that gravity would later amplify. Over millions and billions of years, regions with slightly more matter attracted additional matter. Small differences became larger structures. Clouds became galaxies. Galaxies became clusters. Clusters became superclusters. The immense cosmic web that fills the observable universe may trace its origins back to quantum fluctuations that occurred when the universe was less than a second old. In a very real sense, the largest structures in existence may have emerged from tiny fluctuations within the quantum vacuum. The galaxies overhead, the Milky Way, the solar system, the Earth, you, all connected to events unfolding within the hidden quantum ocean billions of years ago. And this realization transforms our understanding of existence. We often think of reality as something solid, something fixed, something stable. Yet modern physics paints a different picture, a picture in which permanence emerges from constant activity. Order emerges from fluctuations. Structure emerges from uncertainty. The universe appears stable because countless quantum processes average together on large scales. Beneath that stability lies motion. Beneath certainty lies probability. Beneath the familiar world lies a deeper reality that behaves in ways that often defy common sense. Perhaps that is why the quantum world feels so strange. Human intuition evolved to understand rocks, trees, rivers, animals, not quantum fields, not vacuum fluctuations, not probabilities existing simultaneously. Nature at its deepest levels does not seem obligated to match human expectations. And yet, despite its strangeness, it works remarkably well. Every experiment performed over the past century continues to confirm the strange predictions of quantum theory with astonishing precision. The quantum ocean appears real as stars, as real as gravity, as real as the atoms in your body. And perhaps even more fundamental, because without it, the universe we know might never have formed. Yet this hidden ocean introduces another mystery. If empty space possesses energy, if quantum fields fill every corner of the cosmos, then why is the universe expanding the way it is? Why does empty space seem to push galaxies apart? Why does the expansion of the cosmos appear to be accelerating rather than slowing down? Somewhere within the depth of the quantum vacuum may lie the answer, a mysterious force that dominates the universe today. A force that makes up nearly 70% of all cosmic energy, a force we still barely understand. And as we continue our journey, we will encounter one of the greatest mysteries in modern science, a mystery known as dark energy. If you're enjoying this journey through the deepest mysteries of reality, consider subscribing for more cosmic explorations. 8. Space may not be continuous. The smooth universe you experience every day may actually be made of tiny building blocks. Run your fingers across a wooden table. Look at the wall beside you. Gaze at the stars outside your window. Everything appears smooth, continuous, unbroken. Space itself feels like an endless stage stretching in every direction. A vast cosmic arena where galaxies drift, stars burn, and planets orbit. It feels natural to imagine that space extends forever in a seamless way. If you could zoom in closer and closer, you might expect to find more space, and then more space, and then even more. An infinite continuum, a perfectly smooth fabric. For centuries, that is exactly how scientists viewed reality. Space was considered continuous, divisible forever. No smallest unit, no fundamental grain, no ultimate limit. But as physics pushed deeper into the foundations of existence, an unsettling possibility emerged. What if space is not continuous at all? What if reality has a resolution limit? What if there exists a smallest possible distance, beyond which the very concept of space loses meaning? At first, the idea sounds bizarre, almost impossible. After all, we can always imagine cutting something in half, then cutting it in half again, and again, and again. Human intuition suggests the process can continue indefinitely, yet nature often refuses to follow intuition. Again and again, science has revealed that reality operates according to rules stranger than our everyday experience would suggest. Matter, for example, once appeared continuous. Ancient philosophers debated whether objects could be divided forever. Today, we know the answer. Atoms exist, and beneath atoms lie smaller particles. Reality is structured, layered, quantized. Perhaps space itself is no different. To understand why physicists take this possibility seriously, we need to travel toward one of the most extreme frontiers in science. A scale so small that ordinary language begins to fail. A scale known as the Planck length. The Planck length is incredibly tiny, about 1.6 times 10 to the minus 35 meters. The number is so small that it almost defies comprehension. Imagine an atom. Now shrink it until it becomes smaller than a grain of dust compared to the entire observable universe. Then shrink it again and again. Even that comparison struggles to capture the enormity of the difference. The Planck length exists at a scale far beyond anything our technology can directly observe. Yet many physicists suspect it may represent something profound, a fundamental limit, the smallest meaningful unit of distance in nature. Below this scale, space may cease to behave as space. The familiar concepts of location, distance, and geometry may simply stop making sense. This idea emerges because two of the greatest theories in science seem to collide at extremely small scales. One is quantum mechanics, the theory governing the microscopic world. The other is general relativity, Einstein's description of gravity and spacetime. Both theories work remarkably well. Quantum mechanics predicts experimental results with astonishing precision. General relativity accurately describes black holes, gravitational waves, and the evolution of the universe. Yet when physicists attempt to combine them under extreme conditions, problems arise. The equations begin to break down. Infinity appears. Predictions become nonsensical. It is as though the universe is signaling that something deeper remains hidden. Some missing piece of reality has yet to be discovered, and many researchers suspect that the answer involves the structure of space-time itself. Perhaps space is not infinitely smooth. Perhaps it possesses an underlying architecture. Perhaps what appears continuous from a distance is actually composed of tiny building blocks. Consider a digital photograph. Viewed normally, it appears smooth. Curves seem continuous. Edges seem sharp. Colors blend naturally. But zoom in far enough and the illusion disappears. Eventually, you encounter pixels, tiny, discrete units. The image is no longer continuous. Its smoothness was only apparent. Some physicists wonder whether spacetime may behave similarly. At human scales, space appears smooth. At cosmic scales, galaxies move through a continuous universe. But at the deepest level, there may be a hidden pixelation. A granular structure invisible to ordinary observation. A cosmic resolution limit. The idea remains speculative. No experiment has yet confirmed that spacetime is quantized. Yet several promising theories point in this direction. One example is loop quantum gravity. In this framework, spacetime itself consists of tiny, discrete units. Space is not infinitely divisible. Instead, area and volume come in fundamental chunks. Like atoms of geometry, tiny building blocks woven together into the fabric of reality. Another approach emerges from string theory. While very different in its mathematics, it also suggests that our familiar picture of spacetime may not be fundamental. At sufficiently small scales, reality behaves in ways radically different from our everyday experience. The details remain uncertain, but the message is surprisingly similar. Space may not be what it seems, and perhaps the most fascinating implication involves black holes. Black holes push gravity to extraordinary extremes. Their immense mass compresses matter into incredibly small regions. As one approaches the center of a black hole, Einstein's equations predict a singularity, a point of infinite density, a place where space-time itself breaks down. Yet many physicists suspect that singularities do not actually exist. Instead, they may signal the limits of our current theories. A future theory of quantum gravity could replace singularities with something more realistic, something finite, something structured. And if that happens, we may discover that space-time possesses a hidden architecture after all. But the implications extend beyond black holes. They reach all the way back to the beginning of the universe. Because if space has a smallest possible scale, then the earliest moments of cosmic history may look very different from what we currently imagine. The Big Bang itself may not have emerged from an infinitely small point. Instead, the universe may have begun from a finite quantum state, a state governed by the discrete building blocks of spacetime, a state where geometry itself behaved according to quantum rules. This possibility is one reason cosmologists continue searching for clues hidden within the oldest light in the universe. Tiny patterns in the cosmic microwave background. Subtle fingerprints left behind by the infant cosmos. Signals that might reveal whether spacetime possesses a deeper structure. So far, the evidence remains incomplete. The mystery remains unsolved. But perhaps that uncertainty is what makes the question so captivating. We often imagine reality becoming simpler as we investigate smaller scales. Instead, the opposite seems to happen. The deeper we look, the stranger existence becomes. Matter dissolves into fields. Particles become probabilities. Empty space becomes active. And now, even space-time itself appears less solid than we once believed. The smooth universe surrounding us may be an illusion of scale, a grand approximation emerging from deeper microscopic structures, a cosmic image whose pixels are simply too small for us to see. And if that is true, an even more astonishing question awaits. If space itself is built from something deeper, what is that deeper thing? What lies beneath space-time? What fundamental ingredients give rise to the universe we experience? As we continue our journey, we will encounter an idea that challenges our most basic assumptions about reality. An idea suggesting that space may not be fundamental at all. That space-time itself could be an emergent phenomenon, a consequence of something even more profound, hidden beneath the surface of existence. 9. The smallest distance nature allows. There may be a fundamental limit beyond which the concepts of space and distance stop making sense. Imagine shrinking yourself, not to the size of an ant, not to the size of a grain of sand, not even to the size of an atom. Keep shrinking, past molecules, past electrons, past quarks, past everything humanity has ever directly observed. As you descend deeper and deeper into the fabric of reality, you might expect the universe to continue forever. Smaller scales revealing even smaller scales, distances becoming shorter without limit. An endless journey into the infinitely small. For most of human history, this seemed perfectly reasonable. Why would nature impose a minimum distance? Why should reality have a stopping point? After all, when we draw a line on paper, we can always imagine dividing it into smaller pieces, and then smaller pieces, and then smaller still. The process appears limitless. But modern physics has uncovered a strange possibility. The universe may not permit this endless descent. There may exist a smallest meaningful distance, a scale beyond which the very ideas of here and there lose their meaning. A place where space itself dissolves, a frontier where the geometry of reality ceases to behave as geometry at all. And if this limit exists, it could hold the key to some of the deepest mysteries in science. To understand why, we must revisit two extraordinary achievements of human thought. The first is Einstein's theory of general relativity. The second is quantum mechanics. Both theories transformed our understanding of reality. Both have survived every experimental challenge thrown against them, and both appear to describe nature with astonishing accuracy. Yet beneath their success lies a problem. They do not fit together. General relativity describes gravity as the curvature of spacetime. Mass bends space. Space guides motion. Planets orbit stars because they follow curved paths through a warped cosmic geometry. On large scales, the theory works beautifully. It predicts black holes, gravitational waves, the expansion of the universe, entire galaxies moving through the cosmic web. But quantum mechanics tells a very different story. The quantum world is not smooth. It is probabilistic, uncertain, discrete. Particles behave like waves. Locations become fuzzy. Reality itself appears governed by probabilities rather than certainties. And when physicists attempt to combine these two frameworks at extremely small distances, everything begins to break down. The equations produce infinities. Predictions become meaningless. Theories stop working. It is as though nature places a warning sign at the edge of our understanding. Beyond this point, something is missing. Something fundamental. Something deeper. And that missing piece may reveal itself at the Planck scale. The Planck length is often described as the smallest meaningful unit of distance in the universe. It is approximately 1.6 times 10 to the minus 35 meters. That number is almost impossible to visualize. Light can circle the Earth more than 7 times in a single second. Yet the Planck length is so small that a proton appears enormous by comparison. If an atom were expanded to the size of the observable universe, the Planck length would still be unimaginably tiny. It exists far beyond the reach of our most powerful instruments. Yet physicists keep encountering it, again and again, as if nature is quietly pointing towards something important. At this scale, gravity becomes as strong as the other fundamental forces. Quantum effects become unavoidable. Space-time itself may begin fluctuating. The smooth geometric arena described by Einstein may transform into something entirely different. Many physicists suspect that below the Planck length, asking questions about distance may no longer make sense. The situation is somewhat similar to a digital image. From a distance, a photograph appears smooth, continuous, detailed. But zoom in far enough and eventually the pixels become visible. Beyond that point, the image cannot be divided meaningfully. There are no smaller details to uncover. The structure reaches its fundamental resolution. Reality itself may behave similarly. What appears continuous at human scales may reveal a hidden granularity when examined closely enough. A cosmic pixelation woven into space-time itself. Some theories suggest that space may be composed of tiny units linked together in intricate networks. Others propose that space-time emerges from more fundamental structures entirely. Still others suggest that distance itself is not fundamental, but arises from deeper relationships between quantum systems. Although these ideas differ, they share a remarkable implication. The universe may possess a built-in limit, a smallest scale, a final frontier. And that frontier may fundamentally reshape our understanding of existence. Perhaps nowhere is this more important than inside black holes. Black holes represent some of the most extreme environments in nature. Their gravity becomes so intense that space-time bends dramatically. According to classical relativity, matter falling into a black hole eventually reaches a singularity, a point of infinite density, infinite curvature, infinite gravitational force. But infinities are often warning signs in physics. They usually indicate that a theory has reached its limits. Most physicists suspect singularities are not physical objects. Instead, they are symptoms of incomplete understanding. Something else must happen before infinity is reached. Something governed by quantum gravity. Something that becomes important near the Planck scale. If space-time possesses a smallest distance, singularities may disappear entirely. Instead of infinite compression, nature may impose a limit, a fundamental boundary beyond which matter and geometry cannot be squeezed. In this picture, the universe protects itself from mathematical absurdities. Infinity never appears because reality itself has a minimum scale. And the implications extend even further. They reach all the way back to the beginning of time. For decades, cosmologists describe the Big Bang as a singularity, a moment when the universe existed in an infinitely dense state, a point where all known physics breaks down. But if singularities are not physically real, then perhaps the Big Bang was not a true beginning. Perhaps something came before. Perhaps the universe emerged from a quantum state governed by Planck scale physics. Perhaps time itself behaves differently at such scales. Perhaps the question, what happened before the Big Bang, is not meaningless after all. These possibilities remain speculative. We do not yet possess a complete theory of quantum gravity. We do not yet know what truly exists at the smallest scales. Yet every major clue points toward the same conclusion. Reality is deeper than it appears. The smooth space-time of everyday experience may be only an approximation. Beneath it may lie an entirely different layer of existence. A layer where distance loses meaning, where geometry becomes quantum, where space itself ceases to be fundamental. And this realization leads us toward an even stranger possibility. What if space is not the foundation of reality? What if something even deeper exists beneath it? Something from which space-time itself emerges? Because some of the most revolutionary ideas in modern physics suggest exactly that. The universe we experience may not be built from space and time. Instead, space and time may be the result of something more fundamental, something hidden beneath reality itself. And if that is true, then everything we think we know about existence may be only the surface of a much deeper cosmic mystery. 10. When time itself begins to disappear. At the deepest level of reality, time may not exist at all. Few ideas feel more impossible than that. After all, time seems woven into every aspect of existence. You woke up this morning. You listened to these words tonight. Stars are born. Stars die. Galaxies collide, civilizations rise and fall. Everything appears to unfold within time. It feels so fundamental that most of us rarely stop to question it. Space can be difficult to imagine. Quantum mechanics can seem strange. Black holes can feel exotic. But time feels obvious, relentless, unavoidable. The one thing that is always there, ticking forward, moment after moment, second after second. Yet some of the deepest theories in modern physics suggest a possibility so strange that it borders on science fiction. Time may not be fundamental. It may not be one of the basic ingredients of reality. Instead, time might be an emergent phenomenon, a useful illusion, a consequence of deeper processes occurring beneath the surface of existence. And if that sounds unsettling, it should, because removing time changes almost everything we think we know about reality. To understand why physicists take this possibility seriously, we need to start with a simple question. What exactly is time? At first glance, the answer seems easy. Time is what clocks measure. Time is the flow from past to future. Time is the sequence of events unfolding throughout the universe. But when physicists attempt to define time precisely, things become surprisingly difficult. Consider space. You can point to a location. You can measure a distance. You can identify coordinates. Space behaves like a stage. Objects move across it. But time is different. You cannot point to a moment in the same way. You cannot step outside time and observe it directly. You are always moving through it, carried along by something that seems impossible to stop. Or are you? The first major crack in our understanding appeared with Einstein. Before Einstein, most scientists assumed time flowed uniformly throughout the universe. One cosmic clock, one universal rhythm, the same everywhere. But relativity shattered that picture. Einstein showed that time is flexible, stretchable, dependent upon motion and gravity. Two observers moving at different speeds can experience different amounts of time. A clock aboard a fast-moving spacecraft ticks more slowly than a clock on Earth. A clock near a black hole runs differently than a clock far away in empty space. Time is not universal. It is local, relative, personal. This discovery was shocking enough. But it was only the beginning, because relativity revealed something even stranger. Space and time are not separate entities. They are woven together into a single structure, spacetime, a four-dimensional fabric connecting every event in the universe. In Einstein's equations, time behaves almost like another dimension of space, not identical, but deeply linked. And this raises an unsettling possibility. If space can emerge from something deeper, as many physicists now suspect, could time emerge as well? The question becomes even more fascinating when we examine the equations describing the universe at its deepest levels. Many fundamental laws of physics appear surprisingly indifferent to time. Imagine filming two billiard balls colliding. If you play the footage backward, the motion still obeys the laws of physics. Nothing seems impossible. Nothing obviously violates nature. At the microscopic level, many physical processes do not care which direction time flows. The equations work almost equally well forward or backward. Yet our everyday experience feels completely different. You remember yesterday. You do not remember tomorrow. A glass can shatter. The shattered pieces never spontaneously leap together and become a glass again. Time appears to possess a direction, an arrow, a flow from past toward future. But where does that arrow come from? Remarkably, it may not come from the fundamental laws themselves. Instead, many physicists believe the arrow of time emerges from entropy. Entropy is often described as a measure of disorder. More precisely, it measures the number of possible arrangements available to a system. The second law of thermodynamics states that entropy tends to increase. Order naturally gives way to disorder. A neat room becomes messy. Ice melts. Stars burn their fuel. The universe evolves toward greater entropy. And because entropy increases in one direction, we perceive time moving in one direction as well. The future is the direction of increasing entropy. The past is the direction of lower entropy. But this explanation introduces an even deeper mystery. Why did the universe begin in such a low entropy state? Why was the early cosmos so extraordinarily ordered? Because without that initial condition, the arrow of time might never have emerged. The flow of time we experience every day may ultimately depend upon conditions established near the beginning of the universe itself. And this realization leads us toward one of the strangest ideas in theoretical physics. Some equations describing quantum gravity contain no time variable whatsoever. None. Time simply disappears. One famous example emerges from the Wheeler-DeWitt equation, an attempt to combine quantum mechanics and gravity into a unified framework. The remarkable thing about this equation is not what it contains. It is what it lacks: time. The universe is described as a whole, a complete entity, not evolving through time, simply existing. At first, this seems impossible. How can reality exist without time? How can change occur? How can anything happen? Yet some physicists argue that time may emerge from relationships within the system itself. Just as temperature emerges from the motion of countless atoms, just as a wave emerges from countless water molecules, time may emerge from deeper quantum structures. It may not be fundamental, it may be collective, an approximation that appears at large scales, a useful description rather than a basic ingredient. Imagine opening a novel. Every page already exists simultaneously. The beginning, the middle, the ending, all present at once. Yet as you read, you experience the story unfolding sequentially, one event after another. A flow emerges from your perspective. Some physicists suggest reality may work in a vaguely similar way. The universe could exist as a vast structure beyond time. What we perceive as temporal flow may emerge from our position within that structure, not because time fundamentally moves, but because consciousness experiences events in sequence. The idea remains speculative, yet it illustrates how radically our understanding of reality may need to evolve. Because once time becomes emergent rather than fundamental, many familiar assumptions begin to crumble. The distinction between past and future becomes less clear. The concept of beginnings becomes less straightforward. Even the Big Bang itself may need to be reinterpreted. Was it truly the beginning of time, or merely the point beyond which our familiar notion of time ceases to apply? We do not yet know. But the closer physics moves toward a theory of everything, the more frequently time seems to fade into the background, not disappearing entirely, but becoming less fundamental, less absolute, more like an emergent property of a deeper reality. And if time is not fundamental, another astonishing question immediately appears. What exactly is fundamental? What lies beneath both space and time? What deeper framework gives rise to the universe we experience? Because as strange as the disappearance of time may seem, some physicists believe an even more extraordinary possibility awaits. The universe itself may not be the ultimate level of reality. Instead, it may emerge from something far more abstract, something built not from matter, energy, space, or time, but from information itself. And that possibility will take us even deeper into the mystery of existence. 11. The hidden architecture beneath space-time. The universe could be built from structures so strange that they resemble information more than matter. For most of human history, we believed we understood what reality was made of. First, there were the ancient elements: earth, water, air, fire. Then came atoms, tiny building blocks composing everything around us. Later, scientists discovered protons, neutrons, electrons, and eventually quarks. Each generation believed it had reached the foundation, the deepest layer, the final answer. And each generation turned out to be wrong. Again and again, reality revealed another level hidden beneath the one before, another layer, another mystery, another deeper structure waiting to be discovered. Now, after centuries of investigation, physics may be approaching an even more astonishing possibility. Matter may not be fundamental. Space may not be fundamental. Time may not be fundamental. Instead, all three might emerge from something far stranger, something more abstract, something that resembles information itself. At first glance, that sounds impossible. Information feels intangible. A sentence contains information. A book contains information. A computer stores information. But how could information create stars? How could information create galaxies? How could information create reality itself? Yet some of the most important discoveries in modern physics point in exactly that direction. And the story begins with a surprising question. What happens when something falls into a black hole? For decades, physicists assumed the answer was simple. The object disappears, gone forever, lost beyond the event horizon, a one-way journey into darkness. But then a problem emerged. According to quantum mechanics, information cannot simply vanish. The laws of physics preserve information. The details describing a system may become scrambled, difficult to recover, practically impossible to reconstruct, but they should never be completely destroyed. And yet black holes seem to do exactly that. Throw in a book, a spaceship, an entire planet. The information appeared lost forever. This contradiction became known as the black hole information paradox, and solving it would force physicists to rethink the foundations of reality itself. Because if information cannot be destroyed, where does it go? What happens to it? For years, some of the brightest minds in science wrestled with these questions. Then, an extraordinary idea began to emerge. Perhaps information is more fundamental than matter. Perhaps matter itself is simply one way information manifests. The idea sounds radical, but evidence kept accumulating. One of the most famous breakthroughs came from studies of black hole entropy. Physicists discovered something deeply strange. The amount of information a black hole can contain does not scale with its volume. It scales with its surface area. Think about that for a moment. Normally, when you fill a box with objects, the amount you can store depends on the volume inside. A larger box holds more stuff. Simple. But black holes appear to follow a different rule. Their information content is encoded on their boundary, not their interior, their surface. And this led to one of the most mind-bending concepts ever proposed, the holographic principle. The name comes from holograms. A hologram is a two-dimensional surface capable of encoding a three-dimensional image. The information exists on a flat boundary, yet a three-dimensional world emerges from it. Some physicists began wondering whether the universe itself might operate similarly. What if the three-dimensional reality we experience is somehow encoded on a lower dimensional boundary? What if space itself emerges from information? What if reality is, in some profound sense, holographic? At first, the idea sounds absurd. But remarkably, certain mathematical models support it. Some versions of quantum gravity work precisely because information stored on a boundary appears capable of generating an entire spacetime geometry. In these models, space is not fundamental. It emerges. Geometry emerges. Distance emerges. Perhaps even gravity emerges, all from deeper informational relationships. And suddenly, many mysteries begin to look different. Consider space itself. For centuries, we imagined space as a giant container, a stage upon which reality unfolds. But what if space is more like a network, a web of relationships connecting pieces of information? Instead of empty distance existing independently, spatial geometry might emerge from patterns of connection. The closer two regions are connected informationally, the closer they appear in space. Distance becomes a consequence, not a foundation. An effect, not a cause. Some physicists compare this idea to social networks. Imagine millions of people connected through friendships. The network has structure. Clusters emerge. Communities form. Patterns appear. None of those structures exist independently of the connections themselves. They emerge from relationships. Reality may operate similarly. Space could be the visible consequence of deeper informational links hidden beneath the surface. And if that possibility is correct, it transforms our understanding of existence, because it suggests that matter, energy, space, and time are not the deepest ingredients of reality. They may be emergent phenomena, like waves emerging from water, like temperature emerging from molecular motion, like a hurricane emerging from countless interactions between air molecules. The things we perceive as fundamental may simply be large-scale patterns, the visible surface of a deeper structure, a hidden architecture beneath space-time itself. And perhaps nowhere is this idea more powerful than in quantum entanglement. Einstein famously called entanglement spooky action at a distance. When two particles become entangled, their properties remain correlated regardless of distance. Separate them by a room, separate them by a galaxy. The relationship persists. To Einstein, this seemed impossible. Space should separate things. Distance should matter. Yet entanglement appears to ignore those expectations. And modern physics increasingly suggests that entanglement may not merely occur within spacetime. It may actually help create spacetime. Some researchers have proposed that the geometry of the universe emerges directly from networks of entangled quantum information. In this picture, entanglement acts like invisible stitching, threads connecting reality together. The fabric of spacetime itself may arise from these hidden connections, not the other way around. The implications are staggering. The universe may not fundamentally be a collection of objects moving through space. It may be a vast informational structure, a cosmic network, an immense web of relationships generating the reality we experience. Matter becomes information. Space becomes information. Time becomes information. Everything becomes information. Of course, many questions remain unanswered. These ideas remain active areas of research. Scientists continue debating them, testing them, refining them. No one yet possesses the final theory, but the direction is remarkable. The deeper we investigate reality, the less it resembles a machine made of solid parts, and the more it resembles a dynamic informational system, a hidden architecture operating beneath everything we see. And if this hidden architecture truly exists, another extraordinary possibility emerges. What if the universe itself is not the only one? What if different informational structures could generate entirely different realities, different laws, different dimensions, different universes? Because as we continue our journey, we are about to encounter one of the most controversial ideas in all of cosmology. The possibility that our universe may be only one tiny region within a far greater cosmic landscape, a landscape containing countless other universes beyond our own. 12. Are we living inside an emergent reality? Everything around you may be a large-scale illusion emerging from deeper quantum rules. Right now, it probably feels like you're sitting in a solid universe. The floor beneath you feels solid. The walls around you feel solid. Your body feels solid. The earth beneath your feet feels permanent, stable, real. And from the perspective of everyday life, it absolutely is. You can touch it, measure it, build civilizations upon it, trust it to behave predictably. But one of the strangest lessons of modern physics is that reality often looks very different when examined from a deeper perspective. The world that appears solid is mostly empty space. The particles that seem like tiny objects behave like waves. The flow of time may not be fundamental. And now, some physicists are beginning to suspect that space-time itself may not be fundamental either. Instead, the universe we experience may be an emergent reality, a large-scale phenomenon arising from deeper quantum processes hidden beneath the surface. At first glance, this sounds like the premise of a science fiction movie, some kind of cosmic simulation, a giant illusion, a grand trick being played on humanity. But that is not what physicists mean when they use the word emergent. In science, emergence describes something very familiar. In fact, you encounter emergent phenomena every day. Consider a snowflake. A snowflake possesses beautiful symmetry, intricate geometry, complex patterns. Yet none of those patterns exist inside individual water molecules. A single molecule does not contain six-pointed symmetry. The snowflake emerges when countless molecules interact together. The large-scale structure appears naturally from simpler underlying rules. Or think about a hurricane. A hurricane can span hundreds of miles. It possesses shape, behavior, motion. Yet there is no single air molecule that contains the hurricane. The storm emerges from the collective interactions of countless particles. The larger structure is real, but it is not fundamental. And this is exactly the possibility some physicists are now considering for space-time itself. Space may be real, time may be real, but they may not be fundamental. They may emerge from deeper quantum relationships. Much like a hurricane emerges from air, or a snowflake emerges from water, or consciousness emerges from neurons. The idea becomes especially compelling when we examine quantum entanglement. Earlier, we encountered this mysterious phenomenon. Two particles become linked, separated by enormous distances, yet somehow remaining connected. For decades, entanglement seemed like an odd feature of quantum mechanics. Interesting, mysterious, but perhaps secondary. Now, many researchers believe it may be far more important. Some even suspect that entanglement could be responsible for constructing space-time itself. That statement sounds outrageous. How can a relationship between particles create the geometry of the universe? The answer remains incomplete, but fascinating clues continue to emerge. One of the most influential ideas comes from a simple observation. When physicists study certain theoretical universes, they discover something remarkable. The geometry of space-time appears directly connected to patterns of quantum entanglement. Reduce the entanglement and space-time begins to break apart. Increase it and geometry emerges. It is as though space-time itself is woven from invisible threads of quantum information, not unlike a fabric woven from countless fibers. Each thread individually appears insignificant, but together they create structure, shape, geometry, reality. Imagine looking at a tapestry from a distance. You see images, patterns, scenes, but if you move close enough, the image disappears. All that remains are individual threads. Perhaps space-time works similarly. From our perspective, we observe distance, direction, motion, time. But underneath may exist something more fundamental, an intricate network of quantum connections, a hidden architecture from which reality emerges. And if this idea is correct, it changes how we think about almost everything. For centuries, we imagined the universe as a collection of objects moving through space. Planets orbit stars, stars orbit galaxies, galaxies move through the cosmos. Space served as the stage, matter performed upon it. But emergence suggests a radically different picture. The stage itself may be part of the performance. Space may arise from relationships. Geometry may emerge from information. Reality may be less like a machine and more like a process. a dynamic structure continuously generated from deeper rules. The implications become even stranger when we consider black holes. Black holes have repeatedly appeared throughout our journey because they seem to occupy a unique position in physics. Again and again, they force us to confront the limits of our understanding. And once again, they provide clues about emergence. Physicists studying black holes discovered something surprising. The amount of information contained within a region appears proportional to its surface area rather than its volume. This finding helped inspire the holographic principle, the idea that three-dimensional reality may emerge from information encoded on a lower dimensional boundary. If correct, our everyday experience of three-dimensional space could be similar to a hologram. Not fake, not imaginary, but emergent, a higher dimensional appearance generated from deeper informational structures. Much like a holographic image emerges from patterns encoded on a flat surface. And while these ideas remain speculative, they are increasingly taken seriously by some of the world's leading physicists. Not because they sound exciting, but because the mathematics continues producing intriguing results. Again and again, information seems to appear where matter once held center stage. Again and again, spacetime appears less fundamental than previously assumed. Again and again, emergence provides elegant explanations for puzzles that have resisted traditional approaches. Of course, enormous questions remain. What exactly is emerging? What are the underlying quantum ingredients? What mechanism generates spacetime? Why does emergence produce a universe governed by the laws we observe? No one knows. Not yet. The mystery remains open. But perhaps that uncertainty is part of what makes the story so beautiful. The deeper science explores reality, the less ordinary existence appears. The universe is no longer merely a collection of stars scattered through empty space. It is becoming something far more profound. A layered structure, a hierarchy of emergence, a reality where familiar concepts arise from deeper and stranger foundations. Matter emerges, space emerges, time emerges. Perhaps even the laws of physics emerge. And as each layer falls away, we discover another hidden beneath it, another mystery waiting in the darkness, another question stretching beyond the horizon, which naturally leads to perhaps the biggest question of all. If space-time itself emerges from deeper quantum structures, could entirely different space-time structures emerge elsewhere? Could different realities exist, different universes, different laws? Because the next mystery takes us beyond our own cosmos and into one of the most controversial ideas ever proposed in science. The possibility that our universe is only one tiny island in an unimaginably vast multiverse, a cosmic landscape containing countless realities beyond our own. Tell me below, do you think space and time are fundamental, or are they something that emerged later? 13. Beyond the edge of the observable universe. The universe you can see may be only a tiny island in a much larger cosmic ocean. Look up at the night sky for a moment. Every star you can see, every galaxy captured by the most powerful telescopes, every cloud of gas drifting between the stars, every black hole, every planet, every atom that has ever been observed by human beings. All of it exists within a region of space that cosmologists call the observable universe. At first, that sounds like the entire universe, but it isn't, not even close. The observable universe is simply the portion of reality whose light has had enough time to reach us since the beginning of cosmic expansion. It is not the edge of existence. It is the edge of our vision, and those two things are very different. Imagine standing on a beach beside an enormous ocean. You look toward the horizon. The water seems to end in the distance. The world appears to stop. But of course, you know better. The horizon is not the edge of the ocean. It is merely the limit of what you can currently see. The observable universe may be exactly the same. A horizon, not a boundary, not a wall, not an ending. Simply the furthest distance from which information has reached us. Beyond that horizon may lie regions of space we can never directly observe, regions so distant that their light will never arrive, even if we wait forever. Entire realms forever disconnected from our view. And this realization immediately raises one of the most fascinating questions in cosmology. If the observable universe is not the entire universe, How much larger is the real thing? The honest answer is astonishing. We do not know. The observable universe spans roughly 93 billion light-years in diameter. That number alone is almost impossible to comprehend. Light travels nearly 300,000 kilometers every second. Yet even moving at that unimaginable speed, crossing the observable universe would require tens of billions of years. It contains hundreds of billions of galaxies, perhaps trillions, each galaxy containing billions or even trillions of stars. The scale is already overwhelming. Yet many cosmologists suspect this vast region represents only a tiny fraction of the entire cosmos. A single bubble, a single patch, a tiny island surrounded by an unimaginably larger cosmic ocean. The reason comes from one of the greatest discoveries of the 20th century, cosmic expansion. In 1929, astronomer Edwin Hubble found that distant galaxies are moving away from us. The farther away they are, the faster they recede. At first, this seemed strange. Why would every galaxy appear to be fleeing from Earth? The answer, as Einstein's theory of relativity revealed, is that space itself is expanding. Galaxies are not racing through space like cars on a highway. Instead, the fabric of space between them is stretching. Imagine drawing dots on the surface of a balloon. As the balloon inflates, every dot moves away from every other dot. No single dot occupies the center. The expansion occurs everywhere simultaneously. Our universe behaves similarly. And when cosmologists ran the equations backward, they discovered something extraordinary. The universe was once much smaller, much hotter, much denser, leading eventually to the Big Bang. But another realization soon followed. If the observable universe is expanding today, then regions beyond our horizon likely exist as well. Regions whose light simply has not reached us yet. The mathematics never suggests that existence suddenly stops at our cosmic horizon. Instead, the universe may continue far beyond it, perhaps infinitely far, perhaps not. No one knows. Yet even the conservative estimates are staggering. Some calculations suggest the entire universe could be hundreds, thousands, or even trillions of times larger than the observable region. And that possibility transforms our perspective completely, because everything humanity has ever known exists inside this tiny, visible bubble. Every civilization, every species, every mountain, every ocean, every human story, every triumph and tragedy, all confined to a small region of a cosmos that may extend vastly beyond our reach. But the story becomes even stranger, because if the universe extends far enough, extraordinary consequences emerge. Imagine an infinite universe, or even a sufficiently large finite one. Eventually, combinations of matter must begin repeating. The same particles can only arrange themselves in a limited number of ways within a given volume. Given enough space, those arrangements inevitably recur. Somewhere unimaginably far away, there could exist another planet remarkably similar to Earth. Another version of our solar system. Another Milky Way. Perhaps another you. Not because of magic, not because of alternate dimensions. Simply because statistics eventually demand repetition on sufficiently large scales. The distances involved would be incomprehensible, far beyond anything we could ever travel, far beyond anything we could ever observe. Yet the mathematics permits such possibilities. And suddenly, the universe begins to feel even larger than before. Not merely vast, but potentially endless. A cosmic landscape extending beyond every horizon, beyond every map, beyond every conceivable journey. Yet perhaps the most profound implication concerns knowledge itself. There may be regions of reality forever inaccessible to us. No telescope will ever see them. No spacecraft will ever reach them. No signal will ever arrive from them. Not because technology is inadequate, but because the laws of physics impose fundamental limits. Certain parts of the universe may remain permanently beyond observation, forever hidden behind cosmic horizons. This idea can feel frustrating. Human curiosity naturally seeks complete understanding. We want to know what lies beyond the next mountain, beyond the next star, beyond the next galaxy. Yet cosmology confronts us with a humbling possibility. Some questions may never be answered directly. Some regions may remain forever unknown. And perhaps there is something beautiful about that, because mystery has always accompanied discovery. Every time humanity expands its horizon, a larger horizon appears beyond it. Every answer reveals deeper questions. Every boundary becomes a doorway. The edge is never truly the edge. And nowhere is this more apparent than when we consider what may exist beyond the observable universe. Because some theories suggest that beyond our cosmic horizon lies not merely more space, but entirely different cosmic regions, different laws, different physical constants, perhaps even different universes altogether. A possibility so enormous that it challenges our understanding of reality itself. A possibility that leads us directly into one of the most controversial and fascinating ideas in modern cosmology, the multiverse. The idea that our universe may be only one among countless others scattered across a much larger cosmic reality. 14. The possibility of infinite universes. There may be countless other universes where the laws of physics are completely different. Imagine for a moment that everything we have discussed so far is only one chapter in a much larger story. Our universe, our stars, our galaxies, our laws of physics. Everything humanity has ever observed, everything that has ever existed within our cosmic horizon. What if all of it is merely one tiny region inside something far greater? A single bubble floating within an endless cosmic sea. For most of history, the word universe implied everything. The totality of existence, the entire cosmic stage, nothing beyond it, nothing outside it, nothing larger. But modern cosmology has gradually opened the door to a startling possibility. Perhaps our universe is not the whole story. Perhaps it is only one universe among many. Perhaps reality is far larger than we ever imagined. This idea is known as the multiverse, and while it remains controversial, it is not simply science fiction. Remarkably, several independent areas of physics seem to point toward similar conclusions. Not because scientists want multiple universes to exist, but because the mathematics sometimes leads there naturally. And once you begin exploring those implications, the scale becomes almost impossible to comprehend. To understand why, we need to revisit something we encountered earlier: cosmic inflation. Shortly after the Big Bang, the universe appears to have undergone a period of extraordinary expansion. Space itself expanded faster than light. Tiny quantum fluctuations were stretched across cosmic distances. The smoothness of the observable universe emerged. Inflation solved several major puzzles in cosmology, but it also created a new mystery. Because according to some versions of inflation, the process never completely stops. Instead, inflation continues forever in certain regions. While one region slows down and forms a universe like ours, other regions continue expanding. And as they expand, new universes form. Then more, again and again, like bubbles appearing in an endlessly boiling cosmic ocean. Each bubble becomes its own universe, its own spacetime, its own cosmic history, its own observable horizon. From inside one bubble, the others may be forever unreachable, yet they continue to exist nonetheless. If this picture is correct, then our universe may be only one member of an unimaginably vast cosmic family, a single bubble among countless others. And suddenly, a fascinating question appears. Would all those universes look the same? The answer may be no. One of the strangest discoveries in modern physics is that many properties of our universe seem delicately balanced. The strength of gravity, the mass of electrons, the behavior of fundamental forces, the value of physical constants. Tiny changes in these numbers could dramatically alter reality. A slightly stronger gravitational force might cause stars to burn too quickly. A slightly weaker electromagnetic force might prevent chemistry from functioning properly. A different balance between nuclear forces could prevent stable atoms from forming. The universe appears surprisingly fine-tuned, and physicists have long debated why. Some argue that a deeper theory will eventually explain these values. Others propose a different possibility. Perhaps many universes exist, each with different physical constants, different rules, different cosmic architectures. In most universes, conditions may be hostile to complexity. Stars fail to form, atoms become unstable, galaxies never emerge. Life remains impossible. But in a small subset of universes, the numbers align. Complex structures appear, planets form, life evolves, observers emerge, and naturally, those observers find themselves living in one of the rare universes capable of supporting their existence. This idea is known as the anthropic principle. And while it remains controversial, it offers a potential explanation for why our universe appears so remarkably suited for complexity. But the implications become even more astonishing. Imagine a universe where gravity is 10 times stronger. Mountains might collapse under their own weight. Stars might live only a few million years. Life, if it emerged at all, would evolve in radically different conditions. Now imagine a universe where electromagnetism behaves differently. Chemistry itself could change. The periodic table might look entirely unfamiliar. Water might not exist. Carbon-based life might be impossible. Or perhaps entirely new forms of matter would arise, forms we cannot even imagine. Then consider something even stranger. What if some universes possess additional spatial dimensions? Not 3 dimensions of space, but 4, 5, 10. Entire realities structured according to geometries beyond human intuition. Creatures living there, if such beings could exist, might experience reality in ways completely alien to our understanding. The very concepts of distance, shape, and motion could be fundamentally different. The multiverse transforms possibility itself. Every universe becomes a different experiment, a different version of reality, a different set of cosmic rules unfolding across billions of years. And yet, despite how extraordinary these ideas sound, there remains a crucial scientific challenge: evidence. Because science ultimately depends upon observation, prediction, testing. And here, the multiverse faces its greatest obstacle. Most proposed universes lie beyond observation, beyond communication, beyond direct measurement. If they exist, they may forever remain outside our observable horizon. This does not necessarily mean the idea is wrong, but it does make verification extraordinarily difficult. As a result, scientists continue debating whether the multiverse represents physical reality or merely a mathematical possibility. Some researchers view it as a natural consequence of inflation. Others remain skeptical. The debate continues, and perhaps it will continue for decades. Yet regardless of the final answer, the idea reveals something profound about humanity's quest for knowledge. Again and again, every boundary we discover turns out to be larger than expected. The Earth was not the center of the cosmos. The solar system was not the entire universe. The Milky Way was not the only galaxy. The observable universe may not be all that exists. Every horizon expands. Every answer reveals a deeper question. Every discovery opens another door. And perhaps that pattern itself tells us something important. Reality consistently proves larger than our imagination, more mysterious than our assumptions, more expansive than our expectations. But even infinite universes may not represent the deepest mystery, because an even more unsettling possibility remains. What if the multiverse itself emerged from something deeper? What if all universes, ours included, are manifestations of a more fundamental reality? A reality beyond space, beyond time, beyond individual universes altogether. Because as we approach the end of our journey, we arrive at perhaps the most profound question of all. Why does anything exist in the first place? Why is there a reality capable of generating universes at all? And that question takes us beyond cosmology, beyond physics, and toward the deepest mystery human beings have ever encountered. 15. Why our universe seems perfectly tuned for life. A tiny change in nature's constants could have prevented stars, planets, and life from ever forming. Imagine sitting in front of a giant control panel. Stretching across the room are dozens of dials. Each dial controls one of the fundamental properties of reality: the strength of gravity, the mass of electrons, the power of the nuclear forces, the expansion rate of the universe. Now imagine turning one of those dials ever so slightly, not by half, not by 10%, just a tiny adjustment, a barely noticeable movement. the kind of change you might make without even realizing it. According to many physicists, that small alteration could erase every star in the cosmos. Another tiny adjustment could prevent planets from forming. Another could make chemistry impossible. Another could ensure that no living creature would ever exist. And suddenly, a remarkable question appears. Why do the laws of nature seem balanced so precisely? Why does our universe possess exactly the conditions needed for complexity to emerge? Because the more scientists study the cosmos, the more surprising that balance appears. At first glance, the universe does not seem particularly friendly to life. Most of space is empty. Most planets are frozen wastelands or scorching infernos. Black holes roam the darkness. Supernovae explode with unimaginable violence. Gamma-ray bursts can sterilize entire regions of galaxies. The universe is not a cozy place. And yet, despite all that hostility, life emerged. Stars formed, planets assembled, chemistry flourished, biology evolved. Eventually, conscious beings appeared capable of contemplating the universe itself. And remarkably, all of this depends upon a delicate network of physical laws. Take gravity, for example. Gravity is by far the weakest of the fundamental forces. That may sound surprising. After all, gravity governs planets, stars, and galaxies. Yet compared to the electromagnetic force, gravity is astonishingly weak. If gravity were significantly stronger, stars would burn through their fuel much faster. Many would live only a fraction of their current lifetimes. Complex biological evolution might never have enough time to unfold. But if gravity were weaker, giant clouds of gas might struggle to collapse into stars at all. The night sky could remain dark forever. No stars, no heavy elements, no planets, no life. The dial appears balanced within a remarkably narrow range, and gravity is only the beginning. Consider the strong nuclear force. This force binds protons and neutrons together inside atomic nuclei. Without it, atoms would not exist. Matter itself would fall apart. Yet even tiny changes in its strength create enormous consequences. If the strong force were slightly weaker, hydrogen might become the only stable element in the universe. No carbon, no oxygen, no nitrogen, no chemistry complex enough for life. But if the force were slightly stronger, nuclear reactions inside stars would behave differently. The entire process of stellar evolution could change. Again, complexity might never emerge. Now consider carbon itself. Every atom of carbon in your body was forged inside ancient stars. Carbon forms because atomic nuclei possess very specific energy levels. In the 1950s, astrophysicist Fred Hoyle made an extraordinary prediction. He realized that if a particular energy state did not exist inside carbon atoms, the element could not form efficiently within stars. Life would become effectively impossible. The universe would contain almost no carbon. Remarkably, when scientists looked for that energy level, they found it, exactly where it needed to be. The cosmos appeared strangely accommodating, as though nature had left a narrow pathway through which complexity could emerge. Again and again, similar examples appear. The masses of elementary particles, the strengths of fundamental forces, the expansion rate of the universe, the amount of dark matter, the amount of dark energy. Change them slightly and the universe becomes radically different. Sometimes sterile, sometimes chaotic, sometimes short-lived, sometimes incapable of forming any structure at all. This observation has led physicists toward one of the deepest debates in science. Is the apparent fine-tuning real? And if it is, how should we explain it? One possibility is that future physics will reveal a deeper theory. Perhaps the constants of nature are not arbitrary. Perhaps they could never have been different. Perhaps a more fundamental set of laws inevitably produces the values we observe. In that case, the apparent fine-tuning may simply reflect our incomplete understanding. The universe would not be specially adjusted. It would be the only possible outcome. Many physicists hope this explanation proves correct, because it would mean nature is ultimately simpler than it appears. But another possibility remains, one we encountered during our discussion of the multiverse. If countless universes exist, each with different physical constants, then most universes would be lifeless. Most would remain dark, empty, simple. Only a small fraction would permit complexity. And naturally, observers would always find themselves inside one of those rare universes capable of producing observers. Not because their universe was designed specifically for them, but because they could not exist anywhere else. Imagine a lottery with billions upon billions of tickets. The winning ticket does not seem surprising once someone eventually wins. Similarly, a multiverse containing countless universes may naturally generate a few capable of supporting life. We happen to inhabit one of them. This idea is known as anthropic reasoning, and while some scientists find it persuasive, others remain uncomfortable with it. After all, it explains the observed values by appealing to a vast population of unseen universes. The debate remains unresolved, and perhaps it will remain unresolved for generations. Yet regardless of the explanation, the underlying fact remains astonishing. The universe possesses properties that allow complexity to exist. Not merely stars, not merely galaxies, but chemistry, biology, consciousness, thought. Somewhere along the history of the cosmos, hydrogen forged carbon, carbon assembled molecules, molecules learned to replicate. Life evolved, minds emerged. The universe became capable of examining itself. And when viewed from that perspective, the story feels almost miraculous. Not necessarily because it was designed, not necessarily because it was inevitable, but because it happened at all. The odds may have been extraordinarily small. The pathway may have been incredibly narrow. Yet somehow the cosmos found its way through. The stars ignited, the planets formed, life emerged. And billions of years later, a conscious being sits beneath the night sky, asking why. But perhaps the deepest mystery remains untouched. Even if we explain the constants, even if we explain the multiverse, even if we uncover the hidden architecture beneath space-time itself, one question still waits in the darkness. The oldest question, the deepest question, the question that stands behind every other mystery. Why is there something rather than nothing? Why does any reality exist at all? And that is where our journey finally arrives, at the edge of science, at the boundary of human understanding, at the greatest mystery existence has ever presented. 16. The greatest mystery of all. After centuries of science, the deepest question remains unanswered. Why does anything exist at all? Throughout this journey, we have traveled farther than any spacecraft. We have crossed billions of light years. We have witnessed the birth of the universe, explored the first moments after the Big Bang, followed the emergence of matter, watched galaxies assemble, peered into black holes, questioned the nature of space, questioned the nature of time, even questioned whether reality itself is fundamental. And yet, after all of that, after centuries of scientific discovery and some of the greatest intellectual achievements in human history, one mystery remains standing, quietly, patiently, waiting at the edge of understanding. Why does anything exist at all? Not why stars exist, not why planets exist, not why life exists, but why there is something rather than nothing. It sounds like a simple question, almost childlike. The kind of question a curious 7-year-old might ask before bedtime. Yet the deeper we investigate it, the more profound it becomes. Because every explanation eventually leads to another question. Why does the universe exist? Perhaps because of the Big Bang. But then why did the Big Bang happen? Perhaps because of quantum fluctuations. Then why do quantum laws exist? Perhaps because of deeper physical principles. Then why do those principles exist? Again and again, the chain continues. Every answer reveals another layer beneath it. Every explanation opens another door. And eventually we arrive at a place where science itself begins to encounter its limits. Not because science has failed, quite the opposite. Science has been extraordinarily successful. It has explained eclipses, gravity, electricity, evolution, the lives of stars, the age of the cosmos, the expansion of the universe. It has transformed mysteries into understanding countless times. But science operates by describing how reality behaves. It excels at uncovering mechanisms, patterns, relationships, rules. The question of why there is a reality for those rules to govern may belong to an even deeper category, a question so fundamental that we do not yet know whether it possesses an answer at all, or whether the human mind is capable of fully comprehending it. Consider for a moment the alternative. Imagine absolute nothingness. Not empty space, not darkness, not a vacuum, because those are all still things. Space is something, darkness is something. A vacuum still contains physical laws. Instead, imagine genuine nothingness. No matter, no energy, no dimensions, no time, no possibility, no laws, no existence whatsoever. The complete absence of everything. It is surprisingly difficult to picture. The human brain almost rebels against the idea. Every image we create still contains something, some background, some stage, some concept of existence. True nothingness may be impossible even to imagine. And perhaps that difficulty itself is revealing. Because maybe existence is somehow more natural than non-existence. Maybe reality does not require permission to exist. Maybe nothingness is not the default state we assume it to be. Some physicists have proposed ideas along these lines. Certain models suggest that quantum laws naturally allow universes to emerge. Others propose that existence may be inevitable. Still others argue that the question itself may be flawed, because it assumes reality needs an external cause. The truth is that nobody knows, and that honesty is important, because one of the strengths of science is its willingness to admit uncertainty. The greatest scientists in history did not succeed because they claimed to possess all the answers. They succeeded because they followed the questions. And perhaps this is the greatest question of all, the mystery beneath every other mystery. The foundation beneath every foundation. Why is there a universe? Why are there laws? Why is there existence? Perhaps one day humanity will discover an answer. A future theory may reveal principles deeper than anything we currently understand. Future civilizations may look back on our confusion the way we look back on ancient debates about the motions of the planets. Perhaps. But there is another possibility. Some mysteries may never be fully solved, not because they are beyond intelligence, but because they exist at the horizon of what explanation itself means. And strangely, there is something beautiful about that. Because mystery is not the enemy of knowledge. Mystery is what drives knowledge forward. Every major scientific discovery began with someone standing before the unknown, looking into darkness, asking a question, refusing to look away. The night sky itself is a monument to unanswered questions. For thousands of years, human beings have looked upward and wondered. Ancient hunters stared at the stars. Early civilizations tracked the planets. Philosophers debated the origins of existence. Astronomers mapped the heavens. Physicists uncovered the laws governing the cosmos. Generation after generation joined the same conversation, a conversation stretching across thousands of years. And now, for a brief moment, you are part of it too. The atoms within your body were forged inside ancient stars. Those stars emerged from clouds of hydrogen. That hydrogen formed shortly after the Big Bang. The particles that make up your brain were present during the earliest chapters of cosmic history. In a very literal sense, you are part of the universe becoming aware of itself. A collection of ancient atoms asking ancient questions, questions that began long before Earth existed, long before the sun ignited, long before galaxies fully formed. The universe spent billions of years creating the conditions necessary for consciousness to emerge. And now, through countless living minds, it wonders about its own origin. It asks why. It searches for meaning. It seeks understanding. Perhaps that is one of the most extraordinary facts in all of existence. Not merely that the universe exists, but that somewhere within it, beings arose capable of contemplating its existence. Beings capable of curiosity, wonder, imagination, and awe. Tonight, as you lie beneath the same cosmos that inspired generations before you, remember how far this journey has taken us. From the first fractions of a second after the Big Bang to to quantum fields hidden beneath reality, to the possibility of multiple universes, to the deepest question ever asked. And despite everything we have learned, the mystery remains. The universe still has secrets. Reality still has depths we have yet to explore. The horizon still stretches beyond our reach. But perhaps that is exactly what makes it so beautiful. Because a universe with no mysteries would be a universe with no wonder. And wonder may be one of the most precious things conscious beings ever experience. As you drift towards sleep tonight, remember that every atom in your body is part of a story that began nearly 14 billion years ago. We may not yet understand why the universe exists, but perhaps the wonder lies in the fact that we can ask the question at all. Sleep well, and I'll see you on our next journey through the cosmos.